During the summer of 1945, the United States dropped 2 atomic bombs on the Japanese cities of Hiroshima and Nagasaki. The bombs were intended to end the war, yet by the end of that year, 40% of civilians living in Hiroshima and Nagasaki died from the immediate blast, heat, or radiation emitted. Almost 70 years later, people in the area are still experiencing the effects of the bomb, known to be radiation, which is the release of high-energy particles and photons when unstable nuclei disintegrate. Although there is quite a difference between radiation exposure from such a large-scale explosion and the daily exposure from everyday devices like microwaves or cell phones, the biological effects of radiation continue to harm people across the world. The war may have ended, but people are still fighting its everlasting effects. We understand the source of the effects of radiation, but where did our knowledge of radiation come from?
Radioactivity was discovered in 1896 by Henry Becquerel. His experiments involved placing phosphorescent minerals, such as uranium, on a photographic plate wrapped in black paper. Becquerel concluded that regardless of the absence of an energy source such as light, an image of the mineral still appeared on the plate when it was developed. This was due to the radioactivity of the uranium mineral, which gave off energy.
Marie and Pierre Curie expanded on Becquerel's work in 1911 and are most famous for discovering the radioactive materials polonium and radium. In their lab, the Curies observed that uranium electrified the air around it, and also that the amount of radioactivity emitted is directly proportional to the amount of uranium present. The Curies determined that radioactivity is a function of atomic, not molecular, interactions. This discovery was crucial to the development of the atomic bomb.
In 1919, Ernest Rutherford contributed to knowledge about radiation by identifying the 3 decay processes that radioactive elements undergo: alpha, beta, and gamma. Alpha decay produces a helium-4 nuclei, beta decay either produces an electron or a positron, and gamma decay releases energy in the form of a photon.
Each decay process correlates to a different level of penetration according to its energy. Alpha particles cannot penetrate a sheet of paper, beta particles cannot penetrate the human body, and gamma particles cannot penetrate lead. For this reason, Marie Curie's cookbooks, which are still radioactive, are kept in lead-lined boxes, and those who wish to consult them must wear protective clothing. The cookbooks are still radioactive because all radioactive materials have half-lives. A half-life is the length of time for half of the radioactive material to go away. Because such materials have half-lives, which can be as long as 1.9 times 10 to the 19th years, we can never be truly safe from exposure to radiation. Radiation persists beyond the initial moment of impact, which is why the effects of the atom bombs dropped on Japan are still harmful. For this reason, duck and cover techniques used during the Cold War to protect from bombs and radiation have been proven futile and useless.
There was a turtle by the name of Bert, and Bert the turtle was very alert. When danger threatened him, he never got hurt. He knew just what to do. He ducked and cover, ducked and cover.
So, if there is no way to hide from radiation, how safe are we? Biological harm from radiation is directly proportional to one's level of exposure. Prolonged exposure causes a greater amount of damage. A radiation dose unit, known as a gray, represents 1 joule of energy deposited in each kilogram of body mass as the radiation passes through the body. The average person might receive a lifetime dose of radiation from background and medical exposure equal to about 25 centigrays, in contrast to some Japanese survivors of the bombs who received over 450 centigrade. It is this type of increased and prolonged exposure which is concerning.
Biological effects of radiation are due to a process called ionizing radiation. Ionizing radiation causes radiation poisoning by changing the structure of cells in the body. Radiation affects bodily tissue by charging particles, which releases electrons from atoms. The electron and ionized atom, which is positively charged, are both unstable and undergo further reactions. These reactions result in changes in molecules which may be important for the biological functioning of cells.
When radiation affects the body of the exposed individual, the effects are somatic. When radiation affects subsequent generations who may not have experienced direct exposure, the effects are genetic. Low doses of radiation cause radiation sickness. Symptoms include fever, nausea, vomiting, lack of appetite, diarrhea, hair loss, bleeding under the skin, and sores of the mouth and throat. Higher doses of radiation cause cells to denature. These damaged cells try to repair themselves. Although it is rare, mistakes are made during this process, resulting in mutations or genetic abnormalities. Humans exposed to higher doses of radiation are also more likely to develop cancer, although non-cancerous effects from high exposure, such as cardiovascular disease, are likely as well.
Despite radiation's negative connotation and all of these dangerous effects, radiation does have some beneficial uses. According to the United States Nuclear Regulatory Commission, radiation has practical applications in medicine, academics, industry, agriculture, archaeology, space exploration, geology, and more. If we continue to explore these alternative and beneficial uses of radioactive materials instead of using them for destructive purposes, then it is possible to revolutionize the way radiation is perceived.